All right, hello everyone. So today we have a discrete math problem, and we're trying to find 5 to the 2003 mod 7. So in other words, what is the remainder, if any, if 5 to the 2003 is divided by 7, is what we're asking. So your calculator won't be able to do this because it's a rather large number. So what are our tools at our disposal that we could use? And the tool really is going to be Fermat's little theorem. So Fermat's little theorem says the following: if you have a, which is in the set of integers, does not divide p, p being a prime number, then a to the p minus 1 is congruent to 1 mod p. Okay, so how do I use that here? So let's apply the theorem pretty much right away. Now, if I was to try to use the theorem on what I have, given that this information up here, the 2003 mod 7, I could work with a, which is 5, and p, which is 7, and certainly 5 does not divide 7 here. So by Fermat's little theorem, I have to have that 5 to the 6 is congruent to 1 mod 7. Okay, so you take 1 power away from 7, 6, and 5 to the 6 is congruent to 1 mod 7 by Fermat's little theorem. And what we're going to do is, based on that, we're going to build ourselves up to an expression that's equivalent to 5 to the 2003 mod 7. All right, well, let's go ahead and go and do that. So here's what I did. We have 5 to the 2003 is equal to 5 to the 6 all raised to the 333 times 5 to the 5th. How did I get that? Well, what I did was as follows. I took 2003 and divided it by 6. And 6 goes into 2003 333 times, and you have a remainder of 5. Okay. And what I'm going to do with that is as follows. I'm going to take the 5 to the 6 to the 333, and that is actually congruent to 1 mod 7. Why is that? Because if you take 5 to the 6, we know that's congruent to 1 mod 7. And it is the case as well that if you take 5 to the 6 and raise it to the 333, it's congruent to 1 to the 333 mod 7 as well. Okay, but 1 to the 1333, that's just 1. So this is the case right here. Okay, so we have that, and here's what I'm going to say next. Well, if I have 5 to the 6 times 333 is congruent to 1 mod 7, then if I take 5 to the 5th and multiply that here, it's congruent to me saying 1 times 5 to the 5th mod 7. Okay, that is a rule that we have. Maybe it's not written out explicitly in a lot of discrete math classes, but we can do that here essentially, and it works out. So it's like, yeah, just think of it multiplying the congruency on both sides by 5 to the 5th. So that works out, and that's still true. And this side now is like saying 5 to the 2003 is congruent to 5 to the 5th mod 7. And 5,000, we have a rule that says the following. If A is congruent to B mod n, this happens if and only if A mod n is equal to B mod n. Okay, so I'm going to use that theorem here. And essentially here, 5 to the 2003 mod 7 is going to equal 5 to the 5th mod 7. Okay. So if I want to know what 5,000 to the 2003 mod 7 is, all I need to do is calculate 5 to the 5th mod 7. And that's fairly easy to do. 5 to the 5th is 3125. And if you take 3125 divided by 7, let's calculate that real quick. So again, 3125 mod 7. Just do some quick long division here. 7 goes into 31 4 times. 32. Again, 4 times. 4 times 7, 28. And 7 goes into 45 6 times. 6 times 7 is 42. So you have a remainder of 3. So this equals 3. And therefore, 5,000. Sorry, not 5,000. 5 to the 2003 mod 7 is equal to 3. Okay. So just to recap, just to give you like a more general overview of what we did, we went ahead and applied Fermat's little theorem here, which says that 5 to the a to the p, let me go back to the theorem. What it says, a to the p minus 1 is congruent to 1 mod p, or in our case, with a being 5 and p being 7, we plug that in and we got 5 to the 6 is congruent to 1 mod 7. And some people ask me, how do you know that's a and how do you know that's p for a equals 5 and p equals 7? Well, it's a matter of just looking at the expression and asking yourself, well, Fermat's little theorem looks like is given as such, and let's see what I'm given. Well, what's my best guess here that I would have to work with? So yeah, my a equals 5 and p equals 7, and that's what I would use. And then what we did was as follows: we rewrote 5 to the 2003 as a product of two powers. One as a power of 5 to the 6, and then you had some kind of power of 5 to some remainder. That was the 5 here. But the important thing is that you rewrite your power here, the 2003, in terms of the p minus 1 for Fermat's little theorem. So we did that. We said 2003 goes in 6 times into 300 and 2003 divisible by 6, is 333 with a remainder of 5. So by the fact that if you take 5 to the 6 and raise it to the 333, that's equivalent to saying 1 to the 33 mod 7, okay, by what I wrote here. And what that allowed me to do was then multiply the congruency by 5 to the 5th. Okay, there's a rule that lets us do that. So 5,000, 5 to the 2003 is congruent to 5 to the 5th mod 7. And when you have that, that means that by a theorem, again here in red, 5 to the 2003 mod 7 is equal to 5 to the 5th mod 7. So it's the same remainder if you went ahead and took 5 to the 5th and divided by 7. That's what we're saying essentially here. And that came out to be 3. Okay, so the idea is like you break this huge number down to something a little easier to work with. Now, sometimes when you break it down, that where I had that 5 to the 5th, that is still somewhat hard to work with. So you could break it down further. And by transitivity, you know, A implies B, B implies C, you could go ahead and break once you get to the nicest kind of form that you can work with a calculator with, or long division as we did here. That's where you would stop. Okay, so that is the application of Fermat's little theorem to help us get the remainder of a rather large number divided by 7. Okay, thank you for your time.